Welcome to Maths with EJD. In this video, I'll be solving a structured problem continuing in the series of the previous ones I did. And here I have a three-part question. The first one is this. We have to we need to define a stochastic matrix. A stochastic matrix. Okay, so that's the first thing to do. And of course, we need to understand that a stochastic matrix, which is also known as a probability matrix, is a square matrix. It's actually a square matrix. It's a square matrix used in probability theory. Used in probability theory. It is used in probability theory. Of course, what else do we have to know about this? We need to know that each element of the matrix, represents a probability. Each element of the matrix represents a probability. Each element represents a probability. And then more information about it is that in a stochastic matrix, all elements are non-negative. All elements are non-negative. All elements are non-negative. And each row of the matrix, sums up to 1. Each row sums up to 1. Of course, that's not all. We should also know that stochastic matrices, stochastic matrices are commonly used. They are commonly used to model transitions. They are used to model transitions in Markov chains. Markov chains. You know, Markov chains involve a lot of movements. So the model transition in Markov chains where they represent the probabilities of transitioning, from one state to another, from one state to another. Okay, so for example, right, if we can have a 2x2 stochastic matrix, we have a 2x2 stochastic matrix which shows movement in states. Let's say we have states 1 and 2, right? And we already know that all the elements are positive, and the sum of each row of elements in each row is 1. So if this is 1/3, right, that is moving from state 1 to state 1 is 1/3. Moving from state 1 to state 2 will have to be 2/3 because the addition of these two will have to be 1. And then moving from state 2 to state 1, if you say that is, say, 3/5, it means that moving from state 2 to state 2 will be 2/5. So if you add up across the rows, everything sums up to 1, and each element is actually non-negative, that is greater than or equal to 0. So we can also have something like that for 3 by 3 matrix. So, but I mean, for this, I won't worry about that in this situation. Okay, so let's talk about the next question. The next question um, is this. That's the B part of the question now. Obtain the probability generating function, that is PGF. Obtain the PGF of a binomial distribution, binomial distribution, which is B of n comma P. That's the question here. All right, how do we go? We can say here now that okay, to obtain the probability generating function of a binomial distribution Bn comma P, right? So first of all, we say let x be a random variable. Let x be a random variable. Let x be a random variable following binomial distribution. Following binomial distribution with parameters n. N is the number of trials in an experiment, right? Number of trials. N is the number of trials. And P is actually the probability of success. Probability of success on each trial. Okay. So if that is the case, then we need to understand again that the PGF of x, the probability generating function of x, is denoted by g of x of z, and that is summation from k equals 0 to n of the probability distribution, right? Which is probability of x equals k, then z raised to power k. So, but here our particular focus is on the binomial distribution, right? So we need to remember what binomial distribution is, right? So we know that for a binomial distribution, for a binomial distribution, B n comma P, where P of x is equal to k is the let me take that again, where P of x is equal to k is the probability mass function. PMF is the probability mass function, which is PMF of the binomial distribution of the binomial distribution of the binomial distribution So we have that formula for binomial distribution, right? That is probability that x is equal to k is actually the same thing as n combination k, right? N combination k of p raised to power k, then 1 minus p raised to power n minus k, like that, such that g x of z, which we need, is actually the summation from k equals 0 to n, then n combination k, p raised to power k, 1 minus p raised to power n minus k, then multiplied by the z raised to power k, right? From what we have here. So we have p of x equals k, then multiplied by z raised to power k. So this is the p of x, that is p of x equals k, right? then now multiplied by z raised to power k. So that way now we have the probability generating function technically defined. We just need to tidy this up. So you see p raised to power k, z raised to power k, like can go together. So we can say this is summation from k equals 0 to n combination k, then pz raised to power k into 1 minus p raised to power n minus k. And generally speaking, anytime you have any expression in this form, right, you are very free to write it in this form. So you have this 1 minus p. So you have 1 minus p, then added to pz, all raised to power n. And this is the probability generating function for binomial distribution. So whenever you have this expression like this, you can always put it together like 1 minus p plus pz raised to power n. And that is the binomial, that is the probability generating function that is required. Okay, so that takes us to the last question in this area, the last question. So that's question C. Question C says to obtain the distribution, the distribution of the discrete random variable which has the characteristic function. So we have a special characteristic function defined here. That is phi of x of t equals q plus p e raised to power it all raised to power n. So that is the question here, the question C. Okay, and to take care of that, right, to obtain the distribution of a discrete random variable x given its characteristic function q of x of t, which is equal to q plus p e raised to power it or raised to power n. Then, so we can use the inverse Fourier transform. So we can use the inverse Fourier transform. So it's more like here now we have the characteristic function and we need to get the distribution. The distribution is that original expression, like what we just did, where you had p of x equals k, that kind of thing. So we can use so it's more like getting, going back, the reverse. So we can use the inverse Fourier transform, right? So we already know that the characteristic function, right? The characteristic function uniquely determines the probability distribution, the probability distribution of x. That's what the characteristic function does. So, but then the characteristic function phi x of t is defined as phi x of t, which is the expectation of e raised to power itx, the random variable x here now. So that's how that is defined, right? So knowing that, then we need to get the distribution back, right? So using, okay, let me change the color now. Let me say in order to use the inverse Fourier transform, to find the distribution we have inverse Fourier transform, right? We have, okay, let me just tidy that up. We have the inverse Fourier transform given by f of x of x now equals 1 over 2 pi integral from minus infinity to infinity. That's over the whole real line. Then e raised by minus itx, then the characteristic function phi of x of t, all of this dt. That's what we have. So, and since that is the case now, so we already have this defined. So we can actually come here to say that f of x is equal to 1 over 2 pi integral from minus infinity to infinity e raised by minus itx multiplied by the function we have q plus p e raised by it or raised by n dt. So we can actually stop here. This is as good as what we are required to find, the distribution. This is it. But then, of course, if you want to, you can stop here for sure. You can for sure stop here. But then you can actually decide to, see this in terms of binomial expansion. So if you want to expand that binomially, right? So using binomial theorem, right? Using binomial theorem. Mind you, you don't have to go beyond that previous line, but I mean, this is me just adding extra. So using binomial theorem, we can expand. Q plus P e raised power it raised power n to be summation from k equals 0 to n. Then we have n combination k, q raised power n minus k. Of course, q can be I minus p. So we have q raised power n minus k, then p e raised power it all raised power k. So we can have this. And if we have that, we can now then say, and so the distribution f of x of x equals 1 over 2 pi integral minus infinity to infinity, right, of e raised by minus itx summation from n equals k, from k equals 0, to n, then n combination k, then q raised by n minus k, then p e raised by it raised power n. Let me take this up. Raised to power n, then all of that dt. So we have this expression in this form. If you want to follow binomial expansion, don't forget you don't have to come this far. The step before that is okay. All right, so that's how it's been in this place. And you want to go over this as much as possible. So it's clear enough. And of course, all of these things take a lot of practice. So if you have not subscribed to this channel, you want to do that. You want to hit the notification bell so that anytime I release a new video, you get alerted. You also want to like, share, and comment. For instance, this question is actually from one of my viewers. So if you have a question like this or any question you like us to solve, we can always try our hands on that. See you in the next video. Thank you.